Hello, we're doing this physics paper for today. This is May June 2022, variant 4.1 or variant 4.3 as well. They're the same paper as you can see. The Earth has a mass of this, the Moon has a mass of that. It's common with paper 4.3, okay? So we're essentially doing the same paper. Alright, so this is May June 2022, paper 4.1 or paper 4.3. The time is 2 hours. The syllabus changed significantly starting from this year. Some topics were removed, like band theory, electronics, operational amplifiers, communications, amplitude and frequency modulation, etc. Attenuation, those were removed. MRI was removed from medical physics, and um, PET scanning was added instead. And we have another new chapter, which is astronomy. All right, that's the new chapter which has been added. So let's take a look at the marks, the threshold for this paper. So the maximum mark was 100 for paper 4.1 and 4.3. Let's see. A was at 59, B was at 51, C was at 41, D was at 31, and E was at 20. All right. So A star would probably be at around 75. 75-ish. 75, 70 to 80, in that range. Not exactly sure where. Let's begin. This is the new formula sheet. Alright, so let's begin with a common question. Newton's law of gravitation. So this is common for a lot of years. So Newton's law of gravitation states that the gravitational force between 2 point masses is proportional to the product of the masses and inversely proportional to the square of their separation. Interesting point, we had a mark for point masses before, but in this mark scheme it has been changed, right? Also guys, if you like the content, remember to subscribe to the video and subscribe to the channel and like the video. It will help me a lot. Alright. So the gravitational force between point masses is proportional to the product of the masses and is inversely proportional to the square of their separation. Alright, so the gravitational force between 2 point masses is proportional to the product of the masses and inversely proportional to the square of their separation. Use Newton's law of gravitation to show that the gravitational field strength at the distance r away from a point mass is given by this expression. Alright, so let's begin. They're telling us to prove G is equal to Gm by r square, gravitational field strength essentially. So this is quite uncommon. Typically, while teaching this, I do show this, but I haven't seen this before as a proof. So we know that gravitational field strength is force per unit mass, and we also know that the gravitational force is equal to Gmm by r square, don't we? So we can say that G is equal to, I'm substituting instead of F, gmm by r square, right, divided by m. So we can get rid of the m's and we end up with g is equal to gm by r square, shown. Okay, so that's all. So I've basically substituted this over here, right? The Earth has mass 5.98 in 10 power 24 kg and radius of 6.37 in 10 power 6. The moon has a mass of this and a radius of this. The Earth and moon can both be considered as point masses at their centers. Their centers are at a distance of 3.84 in 10 power 8 meters apart. Show that the gravitational field strength at the surface of the moon due to the mass of the moon is this. Sure. So we're going to use G is equal to Gm by R square. So G is equal to, the value of G is 6.67 into 10 power minus 11. You're going to find that in the data sheet above. I just have it memorized, right? G, where is it? Here. All right. So 6.67 into 10 power minus 11 into the mass of the moon, which is 7.35 into 10 to the power 22 divided by R square. The radius is this. So remember, the unit of mass is kilograms and the unit of distance is meters, so we do not need to convert it. Okay, so it's just 1.74 times 10 to the power 6 whole square. Okay, so let's check. 6.67 into 10 power minus 11 into 7.35 into 10 power 22 divided by 1.74 into 10 power 6 whole square. Yeah, so we're getting a value of G is equal to 1.619, which is 1.62 basically unit per kg. So that's shown. So for show questions, make sure to use this value in the next part. Explain why there's a point X on the line between the centers of the Earth and Moon where the resultant field strength due to the Earth and Moon is zero. Interesting. This is a common question. This is a very common question. I always do this question with my students. So basically, if this is the Earth and this is the Moon, for gravitational field lines, the field lines are always directed radially inwards, right? So the neutral point, or the point where gravitational field strength should be closer to the moon. Why? It's always closer to the smaller mass. Why is this? Basically because the field strength of the Earth is greater, right? So if you're at the midpoint, the Earth would be pulling with the greater strength. So it needs to be closer to the moon because the moon is the smaller mass. So we need to compensate for that. So essentially, what we're doing is the at that point the field strengths are equal in magnitude and they're always in opposite direction because the gravitational field lines are directed radially inwards, right? So the fields due to the Earth and the moon have equal magnitudes. We get 1 mark for that. But are in opposite directions, which is why they cancel out. Okay, 2 marks for that. Calculate the distance x from the center of the moon. Interesting. So guys, the distance between the centers, this distance over here, this is basically how much? 3.84 into 10 power 8. 3.84 into 10 power 8. So we don't know exactly, we don't know the exact point where the field strength is 0, right? So why don't we consider this distance to be x, right? So what about this distance then? There's a question where we deal with RE, the radius of the Earth, 60 RE. Basically, the distance between the Earth and the Moon is 60 RE. So there's a question like that. It's quite similar. So the distance at the point where field strength is 0 to the center of the Moon is x. So what about, why am I considering this to be x? Because this point over here, we are considering it from the center of the moon. So what about this distance? This should be 3.84 into 10 to the power 8 minus x, right? The distance on the left hand side. This is the essential point. Okay, so what we need to do is, we know that g is equal to gm by r square, right? So the gravitational field strength of the earth should be equal to the gravitational field strength of the moon at point x, right? So the gravitational field strength of the earth is g times the mass of the earth divided by 3.84 times 10 to the power 8 minus x whole square is equal to g times mass of the moon by x whole square. So what's the mass of the earth? It's 5.98 into 10 power 24. So we can get rid of the g's. 5.98 into 10 to the power 24 divided by 3.84 into 10 power 8 minus x whole square is equal to the mass of the moon is 7.35 into 10 power 22. Okay, divided by x square. Following this step, we need to root over the other side. Okay, so we end up with this: x divided by 3.84 into 10 power 8 minus x is equal to root over 0.01229. So root over answer is x by 3.84 into 10 to the power 8 minus x is equal to 0.11086. Okay, so x equals to 0.11086 times 3.84 into 10 to the power 8 minus 0.11086x. So bring the x on one side. X plus 0.11086x equals to 0.11086 times 3.8 into 10 to the power 184 into 10 to the power 8. Or if you take x common, we end up with 1 plus 0.11086 is equal to this one over here. Okay, so x is basically equal to 0.11086 times 3.84 into 10 to the power 8 divided by 1.11086. Okay, so go for that. Your calculated answer multiplied by 3.84 into 10 to the power 8 divided by calculated answer plus 1, which is 3.83 into 10 to the power 1, 2, 3, 4, 5, 6, 7. 3.83 into 10 to the power 7. So let's look at the data. So your answer depends on the minimum number of significant figures. So the minimum number is 3SF. So you can opt for 3SF, that's totally fine. But they've given a 2 significant figure answer. So a 2 significant figure answer is almost safe all the time. Okay, so you can write 3.83 into 10 to the power 7 because we have been using 3 significant figures as our minimum number in the data. So we're just gonna opt for 3.8 into 10 to the power 7, but this answer would have been fine as well. I'm just writing this because it was in the mark scheme. Okay, off to question number 2. A sphere of mass 1.6 in 10 power minus 10 kg has a charge of 0.27 nanocoulombs 10 to the power minus 9. The sphere is in a uniform electric field that acts vertically upwards as shown in the side view. The force exerted on the sphere by the electric field causes the sphere to remain at a fixed vertical height on a horizontal plane. Okay. So this is the side view. The force exerted on the sphere by the electric field causes the sphere to remain at a fixed vertical height in a horizontal plane. Do you guys understand what that means? So this is the plane in which the sphere moves. This is the horizontal plane, so it's basically rotating like this on this plane. This is the movement, because we can't change this plane of motion. We have to be on this plane. All right, we aren't going up, down, left, or right. we're actually rotating clockwise or anti-clockwise on this plane if we're viewing it from the side. Okay, and if you have your eye above, if you're viewing it from above, if you see it like this, you're gonna see this circular motion. Do you guys understand? And look at this, if you view from above, the electric field lines are penetrating your eyes, right? That is why when we see it from above, we see that the electric field lines are coming out of the page. If you're looking at the screen right now, if you're looking at my video, they're going to penetrate your eyes because you're looking at the screen and the field lines are going to your eyes. Does that make sense how we're viewing this from above over here? And if you see it horizontally, then you're going to see that it's rotating around this plane. Okay, so there's a uniform magnetic field in the region of the electric field. The sphere moves at a speed of 0.78 meter per second in the horizontal plane. The magnetic field causes the sphere to move in a circular path of radius 3.4 meters as shown in the view from above. Okay, so this is a question on magnetic field. A magnetic field is a region of space where moving charge experiences force, right? So this is our radius. Interesting question. Hard to comprehend. Determine the direction of the uniform magnetic field. Okay, so you got to use your left hand. Use your left hand. We are going to use the left hand rule. So we have the thumb, index finger, middle finger. So father, mother, child. So the thumb is force, the index finger is the magnetic field, and the middle finger is the direction of current. Okay, so as you can see, our particle, the sphere over here, it's actually experiencing a force in this direction. This is the direction of the force to the right, and the middle finger is the direction of the current or the electric field line. Sorry, the middle finger represents the direction of current, or and the index finger represents the direction of the magnetic field line. So we are supposed to find out the direction of the index finger, and the middle finger represents the direction of the current. Okay, conventional current basically. All right. So let's see how to do this. So your thumb should be pointing to the right, and the middle finger should be pointing towards you out of the screen. If you're doing this on the screen, okay, your thumb, this is your thumb, it should be pointing to the right, okay, and your middle finger should be pointing out of the page or out of the screen. Okay, your thumb should be pointing on the right and the middle finger should be coming out of the page, just like this, the electric field line, because the middle finger denotes the electric field line. So middle finger out of the screen or out of the page, and the thumb should be pointing towards the right. Where is the middle finger, where is the index finger located? Isn't it going downwards? This is the direction of the index finger, right? So thumb on the right, middle finger out of the screen or page. So the index finger should be pointing vertically downwards, and that is the direction of the magnetic field line. Okay, it should be on this direction. All right, so it should be vertically downwards or just downwards. So why is the motion of the sphere in the horizontal plane circular? They want an explanation. So what is this motion? This is circular motion. When do you experience circular motion? What is the origin of circular motion? Basically, if it's experiencing a centripetal force which is directed towards the center, and the centripetal force is perpendicular to the velocity. That's the main reason. Okay. So the magnetic force is basically perpendicular to the velocity. That is why. The magnetic force is perpendicular to the velocity. Okay, so that's the reason why you're gonna have circular motion whenever the force is perpendicular to the velocity, and that magnetic force actually provides the centripetal force. And it can be 3 marks sometimes. This question can be of 3 marks. Then you need to say that the magnetic force is of constant magnitude. All right. Okay. So the magnetic force on the sphere is perpendicular to the velocity, to its velocity. We get 1 mark for that. So the magnetic force provides the centripetal force. All right, so we get 2 marks for that. And typically, if it's worth 3 marks, then you have to write something else. The magnetic force has constant magnitude. Okay, so if you did not write this, you'd be losing the 3rd mark. But here, this was also another option for the 2nd mark. Because if the force was not constant, the radius would differ. Do you guys understand? That's the logic basically. So middle finger out of the page, motion to the right, and index finger vertically downwards. That's the direction of the magnetic field. So the thumb represents motion. Okay. Calculate the strength of the uniform electric field. Great. So basically, this charged sphere, right? So this is an electric field. That means the positively charged plate is over here, and the negatively charged plate is over here. This would typically cause our sphere to move up or down, right? Since it's charged, it does have a charge, right? But since it's not moving up or down, since it's remaining on this horizontal plane, what does that mean? Since it has a positive charge, it should experience an electric force upward, and the weight should be downwards, right? So since it's not moving up or down, the net upward force is equal to the net downward force. Do you guys understand? That's the logic behind this. So we need to say that the electric force is equal to the weight, or F is equal to EQ, right? Electric force equals to EQ, and the weight is mg. So the electric field strength will basically be equal to mg by q. So what is the mass? The mass was 1.6 into 10 power minus 10, and the charge was 0.27 nanocoulombs. So E is equal to 1.6 into 10 to the power minus 10, 2SF, right? Yeah. Into 9.81 divided by Q, which is 0.27 into 10 power minus 9. Tricky sum, tricky sum. I haven't seen this before. This is the first iteration. All right, so I'm getting an answer of 5.8. 2SF because the data is 2SF. Great. By considering the magnetic force on the sphere, show that the flux density of the uniform magnetic field is 0.14. All right, so we know that the magnetic force, provides the centripetal force, right? We've stated that before. So we know that the magnetic force for a charged particle is BVQ, and the centripetal force is mv squared by r, don't we? Now we know that the radius is 3.4. So let's go for it. B times, do we know the velocity? Yeah, we do. 0.78. Okay, so B into 0.78 in the charge, which is 0.27 into 10 to the power minus 9, is equal to the mass, which is 1.6 into 10 power minus 10. We can actually get rid of one of the velocities, my bad. If we get rid of this, we end up with BQ is equal to mv by r, or B is equal to mv by qr. Okay, so B is equal to 1.6 into 10 power minus 10 into 0.34 meters divided by Q, 0.27 into 10 power minus 9 times R, which is, wait, this is BV, right? My bad. So the numerator should be 1.6 into 10 power minus 10 into 0.78. Yeah, this should be 0.34. Okay, let's go for it. 1.6 into 10 power minus 10 to 0.78. All right, we're getting 0.14 Tesla shown. Great. That's all for question 2. Question 3. State what is meant by an ideal gas. So an ideal gas is basically a gas that obeys PV is proportional to T, where P is equal to pressure in Pascal, V is equal to volume, and T is the temperature in Kelvin, or the thermodynamic pressure. Okay, really important. Calculate the amount N of gas. Okay, so we know that PV, small p, my bad, PV equals to nRT. So N is equal to PV by RT. So the value of P is already in pascals, 1.2 in 10 power 5. The volume is in meter cube already, so that's fine. Now the temperature is in degrees Celsius, so we need to find it in Kelvin. That's basically 273 plus 17, and the value of the molar gas constant is 8.31. This is also given in your data sheet. I have it memorized. So 1.2 into 10 power 5 times 0.24. Answer divided by 273 plus 17 is 290 times 8.31. I'm getting an answer of 11.95. So since our minimum data is of 2 SF, we're going to go for 12 moles. Clear? Okay, this is one of my favorite questions. The change for a gas, the change in internal energy over a one whole cycle. The gas undergoes 3 successive changes as shown in figure 3.1. All right. So you guys need to remember that the total internal energy change for one cycle, right, from A to B, B to C, and C to A is in fact 0. The total change is 0. So the initial state is represented by point A. The gas is cooled at constant pressure to point B by the removal of 48 kilojoules of thermal energy. Okay. So according to the first law, we know that del U is equal to del Q plus del W, where Q is thermal energy supplied to the gas and W is work done on the gas. So from A to B, it is cooled, so 48 kilojoules of thermal energy is lost. The gas is then heated at constant volume. Okay, so we know that work done by a gas or on a gas is equal to P del V, right? So if volume is constant, if volume does not change, then no work is done on the gas or by the gas. If del V is 0, then del W is also 0. This is a must, we need to know. So for B to C, actually, del W equals to 0 because volume was constant. Great. Finally, the gas expands at constant temperature back to its original pressure and volume at point A. During this expansion, the gas does 31 kilojoules of work. So since the gas is expanding, when a gas expands, the volume increases. If volume increases, remember, whenever the volume of a gas increases, right? If volume increases, work is done by the gas, so W is negative. Okay, we need to remember that. So this one is a negative energy. So increase in volume is negative work done, and decrease in volume is work done on the gas. Show that the magnitude of the work done during change A to B is 19.2. Okay. So from A to B, the gas is cooled at constant pressure. Okay, so A to B, what's the change? We go from 0.24 to 0.08. All right. So we just need the magnitude, right? So we're just going to go like this. Work done is equal to P del V. So the pressure is constant at 1.2 into 10 power 5. So 1.2 into 10 power 5 times the change in volume, which is 0.24 minus 0.08. So since volume decreased, work is in fact done on the gas. 0.24 minus 0.08 times 1.2 into 10 power 5. That's actually 19,200 or 19.2 kilojoules. Alright, shown. Complete table 3.1 to show the work done on the gas, the thermal energy supplied to the gas, and the increase in internal energy of the gas for each of the changes. This is my favorite question. So we need the power of intuition to figure this out. So let's do this step by step. So for A to B, since volume decreased, if volume decreases, work is done on gas, so that is a positive change. So I'm gonna go for, we just found it out, it's plus 19.2 kilojoules, okay? And we know that del U is equal to work done, del W plus del Q. So if you add them up, 19.2 minus 48, that gives us a value of minus 28.8, okay? I think this is the fifth time that I'm seeing this question. There was also a question like this in March, Feb 2022, and in previous years. Okay, you should be well acquainted with this by now. So if you haven't seen them already, please do see my other videos. I'll link them on the top. So for BC, I already told you something. Since the volume was constant, the work done on the gas was in fact zero, and it was cooled apparently, right? Where it was heated. Okay, so in the first phase we lost. So for B to C, we don't know the change in thermal energy, do we? Okay, we don't know that yet. Then what about the last step? Finally, the gas expands at constant temperature back to its original pressure and volume at point A. During this expansion, the gas does 31.6 kilojoules of work. Okay, so it's minus 31.6. Great. Okay. So the initial state is represented by point A. It is cooled to go to point B, which is why this was minus 48 and the work done on the gas was plus 19.2. Then from B to C, what happened? The gas is then heated at constant volume to point C. Okay, so since it had constant volume, we opted for zero work done. All right. Do you guys understand? Now what? At the end, finally the gas expands at constant temperature. Okay, so this is a key point. Back to its original pressure and volume at point A. During this expansion, the gas does 31.6 joules of work. So remember I taught you something? When volume remains constant, work done is zero. Similarly, here we have the gas expands at constant temperature back to its original pressure and volume. So temperature usually has a relationship with kinetic energy. Okay, it has a relationship with kinetic energy. And this is a tricky one. I haven't seen this iteration before. This is tricky because these parts are common. We've already done these. We have done this before. Typically in these questions we get this point in the question where they say that the gas is heated suddenly or something. So if a gas is heated suddenly, or if it expands suddenly, if it expands or contracts suddenly, no heat is gained or lost. You will see that wording in some questions. Okay, but here it's a different iteration. I haven't seen this before, so this is new for all of us. So these four, how to find these? Okay, so let's do this slowly. So you guys need to understand that when you come to this last point, right, the net internal energy change must be zero. Like all three of these need to add up to zero, or else the cycle won't be complete. I told you guys that initially. Okay, the total change needs to be zero. Now this is an ideal gas, guys. So typically the definition of internal energy is sum of kinetic energy and potential energy. Okay, sum of Ke plus Pe is your internal energy, the random distribution. But since this is an ideal gas, it has no intermolecular forces of attraction, so the internal energy is totally equal to the kinetic energy. Now I was telling you something, right? Basically, in the last step, this is from A to B. This is from B to C, and this is from C to A again. In the last step, there was constant temperature. As a result, I was telling you guys that Ke is constant. So think about it. If Ke is constant, what is the change in del U? No change in Ke, and there's no P since it's an ideal gas. So there's no change in U. So basically, U remains constant, right? For the last change from C to A. So U actually remains constant. And since I told you that we are returning to the original point, A to B, B to C, and C to A, the net change must also be 0. This net change must be 0. How is that possible? Minus 28.8, if this is x plus 0 is equal to 0. So what's the value of x? X is equal to plus 28.8. That is the only possible way. So this needs to be 28.8. Interesting, right? It's a bit difficult. Okay. Now let's do the next part. So what were the marks for? So if you wrote 19.2 and 0, you'd get 2 marks out of 5. Those are the first 2 marks. Then if you wrote 0, the 0 I wrote just now, in CA you'd get 1 mark. And for 31.6, what is this? We'll get another mark. So basically, all these added up are equal to 0, right? Because I told you we're returning to the original temperature and pressure. There's also another thing that we need to use, which is this plus this, these two are equal to this over here. Basically, W plus Q, del Q plus del W is equal to del U, right? So we can use that. So for example, if we name this Y, okay, so 0 plus Y is equal to 28.8. So what is the value of Y? It needs to be 28.8. This is a must, right? So Y is actually 28.8. Similarly, if we name this Z, we can say that minus 31.6 plus Z equals to 0, right? So Z needs to be plus 31.6, okay? So Z is in fact plus 31.6, all right? So this is the only way we end up with the correct answer. So this is how I approach this. I knew this because we found this out above. Then I added these two to get this value, okay? And I got this afterwards because I knew that from B to C the volume did not change, so the work done would be 0. So now we were left with these 4. We didn't know how to do this. So how are we approaching this actually? Basically, we know that temperature is constant for the change from C to A. Since T is constant, K is also constant. So del U is also constant, so U is 0. So I got this first, okay? Next, what did we do? We knew that the summation of these three had to be 0. That's how I got this one. Then we knew that this plus this had to be equal to this. We got this one. And this plus this had to be equal to this. So we got the other one. So that's it. So this was a tough iteration in the sense that you never had to know that when temperature was 0, the change in U was 0 for this table. But anyway, the other parts, adding these up, adding these two to get the other one, that was a common part. Okay, so this was a bit difficult compared to the other ones. Okay, interesting sum. Moving on to question number 4, simple harmonic motion. A pendulum consists of a bob, small metal sphere attached to the end of a piece of string. The other end of the string is attached to a fixed point. The bob oscillates with small oscillations about its equilibrium position as shown. Great. The length of the pendulum measured from the fixed point to the center of the bob is 1.24, okay? The acceleration A of the bob varies with its displacement x from the equilibrium position, okay? This is simple harmonic, clearly. It can be seen from the diagram. It's symmetrical. State how figure 4.2 shows the motion of the pendulum is simple harmonic. So we need to mention 2 points. It's a straight line passing through the origin, which shows that A is proportional to x, and the negative gradient indicates that they're in opposite directions, right? So we can say that the straight line through the origin shows that A is proportional to x, and the negative gradient shows that A is in opposite an opposite direction to x. Okay, so we've proved that A is proportional to minus x. That's all. Use figure 4.2 to determine the angular frequency. So omega is equal to 2 pi by t, or 2 pi f basically. So we know that A is equal to minus omega square x, right? If we remove the proportional sign and introduce a constant, so omega square or minus omega square is basically our gradient. Okay, so why don't we find out the gradient of this graph? So how should we write this really? This is what you should write. You should go for this. A is proportional to minus x, so A is equal to minus omega square x. You should write this. Then you should mention that omega square is equal to minus gradient, right? Here, the value of omega square is equal to minus the gradient. Okay. So let's find out the gradient. So let's use these points. Like for example, we can use this 0.05 and 0.4. 0.4, 0.05. Okay. So let's go for that. So gradient equals to 0.40 divided by 0.050. This is basically equal to omega square. So omega is equal to root over 0.40 by 0.050. Okay. So 0.4, 0.05, root over answer, 2 root 2. Omega equals to 2 root 2. We can't write that. We need to write it down to 2SF. So that's 2.8. Okay. Angular frequency is related to the length of the pendulum by this equation, where k is a constant. Use your answer in B to determine k. So we know the value of L. It's 1.24 meters, right? So omega equals to root over k by L. So 2.8. We're going to use our calculator answer though. Is equal to, never use the rounded off answer. Is equal to k divided by, what was the answer? 1.24. Or basically omega square is equal to k by L, right? So k is equal to omega square L. Right. So we know the value of omega square was, this, right? 0.40, 0.4 by 0.05, which is 8. So k is basically 8 is the unit, fine, meters and meters per second square. Yeah. So 8 times 1.24, okay? Or 2.8 square times 1.24, same thing. So 1.24 times 8 gives us a value of 9.92. So k is equal to 9.9. So the unit of omega, right? So the unit of omega was meter. Omega square was meter is to the power minus 2 divided by meter. So it's basically second to the power minus 2, right? Omega square is second to the power minus 2, because that's angular frequency. Okay. So k, what is this k actually? You need to understand that. So omega is 2 pi f, right? So it has a unit of s minus 1. So omega square has a unit of s minus 2, and L has a unit of meter. So if you combine omega square and L, you end up with meter per second square. So that's the unit. So 9.9 meter per second square. Was this a show question, by the way? They've given the answer as 9.7 actually. 2.8 square times 1.24. We get an answer of 9.7. So interesting fact, they went for this. K is equal to 2.8 square times 1.24. 2.8 square times 1.24. which is 9.7. But if you use the exact answer, it's 9.9. Typically, in most mark schemes, they do use the exact answer. Do you understand? So this is a bit strange. Typically, we'd go for the exact answers. There are a few anomalies every year. Like in a particular question, they don't use the exact one. So it's a bit strange. So just go for one, just learn one. In the questions where they tell you to show a particular answer, go for the rounded up one. But in general, we typically write down we use the exact one. Okay, next one. While the pendulum is oscillating, the length of the string is increased in such a way that the total energy of the oscillations remains constant. So I'll just explain the qualitative effect of this change on the amplitude of these oscillations. Okay, so we know that the energy of oscillations is basically E is equal to half m omega square x naught square, right? So what happened? We have increased the length of the string while keeping the energy constant. What happens to the amplitude? Okay, so what's the relationship of omega and length? Omega is k root over k by l. So omega square is equal to k by l. So can't we write this? E is equal to half m k by l times x naught square. So what happened really? We've increased the length of the string. So if you increase the denominator, energy is supposed to decrease, right? So how are you going to keep the energy constant? We need to balance this change out. If you increase the denominator, you need to increase the numerator as well, right? So what can we do to the amplitude? We can also increase the amplitude. If you increase the amplitude, it can counteract the increase in the denominator, the length. As a result, energy of oscillations remains constant. Okay, so that's the logic behind this. So we can say that increasing L causes omega to decrease, or you could opt for what I was doing on the right hand side, or you could say that energy is equal to half m omega square x naught square, which is equal to half m um, k by l x naught square, right? And L increases. So to balance it out, what's the second point? We need to say that. So amplitude increases, to balance this change out. So that's that. Okay, so we're done with 4 questions. How many do we have actually? It's quite a long paper. We have 10 questions in total. Okay, let's continue. I'm doing 5 right now. Figure 5.1 shows 4 diodes and a load resistor connected to a continuous circuit that is used to produce rectification of an alternating voltage. What is meant by rectification? Interesting. So it's basically conversion from alternating current to direct current. That's it. What is the type of rectification? If you use 4 diodes, that's actually full wave. This is full wave rectification. Okay, common questions. So till now, I think, okay, I'm gonna give an overall, comment on the paper after I'm done with it. But some parts of it are a bit difficult. I would agree to that. Next, a sinusoidal alternating voltage. So my students actually in our region, in the Southeast Asian region, we actually give the variant 4.2. So they gave the 4.2 variant, 4.2 paper. So they were crazy after the exam. They said it was really tough. But a lot of them did end up getting A stars since the threshold was so low. So a sinusoidal alternating voltage is applied across the input terminals x and y. The variation with time t of V in is given by this equation, where V in is in volts and t is in seconds. On figure 5.1, where's 5.1? Label the output terminals P and Q with their appropriate symbols to indicate the polarity of the output voltage. Great. So let's do that. What if this terminal was positive? Let's go. This goes out here. So now which diode should we choose? So we can't take this, right? So we need to take this one. Now we can't take this, so we need to go down, right? So we're going down here. So this is our positive terminal, this is our negative terminal. So if you go out now, which one should you take? You actually cannot be taking this, because then you'd be returning to the same positive terminal. So we're gonna opt for this one over here. Now we won't be taking this, because then we return to the positive terminal. So we're gonna go for this over here. Okay, so that's that. And I can show you the other way around. So in this case, we use this one and this one. Okay, now when the current switches, we're going to use this and this. I'm going to show you how. If this was the positive terminal and if this was negative, how would we be doing this? I'm going to show you that it remains the same at the end. So current would come out from here. It would go here. We take this terminal, right? See, here you go. At the end, this is still positive. This is negative. Then we come out here, go down here, go up here, and yeah, come back over here. That's it. So it doesn't depend on our input really. Even if our input alternates, we are going to have same outputs in our terminals. So that is the basic logic of full wave rectification, right? And in half wave rectification, we simply use one diode. As a result, we don't get the full sine wave rectified. We only get half of the wave rectified. Okay, so yeah, that's it. So we have to use plus and minus. So Q should be labeled with a plus and P should be labeled with a minus. That should be your only labeling. P as plus and sorry, P as minus and Q as plus. That's it. Next, the magnitude of the output voltage varies with time t as shown. On figure 5.2, label both the axes with the correct scales. What? Use the space below. Okay, scaling, right? Scaling. So let's see. We can use this place for working. The equation is V in is equal to 6 sine 25 pi t. V in is equal to 6.0 sine 25 pi t. So basically, the output voltage, the peak output voltage, this is very important. This value, this is your amplitude essentially. You guys know about trigonometry, right, from P1. So suppose you have y is equal to 2 sine x, right? So 2 is your amplitude. So this is basically the amplitude. This one is basically the amplitude. So this should be 6. So if this is 6, how should we label the x's? Each box is like 2 units, right? So 1, 2, 3, 4, 5. This is 2, this is 4, and this is 8, right? So you can label it like this 2, 4, 6, 8, or they just want this. This should be 4 and this should be 8. That's it. You could label 2 and 6. That's fine. Next, use the space below for it working. We need the time period now. So this is one time period, right? So let's see how that happens. So the main equation is V is equal to V naught sine omega t. So do you see this part over here? This is essentially your omega. This is essentially your omega. Okay. This part is our omega. So we know that omega is equal to 2 pi by the time period, right? So omega should be 25 pi is equal to 2 pi by t. We can get rid of the pi. What do we end up with? T is equal to 2 by 25. How much is that? 2 by 25 is 0.08 seconds. So this is basically 0.08 seconds, one time period. So this is 0.04 seconds, right? We don't need to write the second. So this is 0.02, 0.06, 0.10, 0.12. That is all. Do you guys understand? That's it. Now, part C. Okay, so we have a capacitor. The output voltage in B is smoothed. We use capacitors for smoothing. So it's smoothed by adding a capacitor to the circuit in figure 5.1. The difference between the maximum and minimum values of the smoothed output voltage is 10% of the peak voltage. Okay, guys, so 10% of the peak. How much is that? 10 divided by 100 into 6 is 0.6 volts. Okay, so this is the difference between the maximum and minimum. So since the max is 6, what should the minimum be? It should be 6 minus 0.6, which is 5.4 volts. Okay, so the maximum is 6 volts and the minimum is 5.4 volts. That is some information we got. On figure 5.1, draw the circuit symbol for a capacitor showing the capacitor correctly connected into the circuit. The capacitor should always be connected parallel to the load. Okay, so it should be parallel to the load using the correct symbol. It's like this. We get 1 mark for that. Now for the next part, sketch the variation with time t of the smoothed output voltage. So the maximum is as usual 6, but the minimum is 5.4 rather than 0. When should it reach 5.4 though? This is the important part. So 5.4, how much is that? Basically, this is 6, right? So this is 5. How much is each box worth? Think about it. This is 4.2, 4.4, 4.6, 4.8, 5, 5.2, 5.4, 5.6, 5.8, 6. So where is 5.4 located anyway? This is 5, this is 5.2, 5.4. So it's basically 1.5 boxes. This is 5.4. So this, our graph cannot go below this line. Okay, this is our endpoint. Our graph cannot go below this line. Tricky. I haven't seen this variation. So let's go with t, the variation with t. So typically start from this point over here. So they've said that we need straight lines or curves with negative decreasing gradients drawn between adjacent peaks from the top of first peak to meet the line going up to the next peak. So we need negative decreasing gradients. So it's basically like this. Here you go. It's going to get flatter over time. Here. Okay. So you need to complete this for the other ones. Or you could draw a straight line. That also works if you're not confident. Then it's gonna copy this point. Okay. Wait, let me use a different color for this part. Okay, so it's further here. It's further down here. So it's gonna be like this. Wait up. The next peak should be around here, right? So we're gonna hit it right here. So it's gonna be like this, like this. Okay. We can't hit that point over there. Wait. Damn, this is hard, bro. Okay, yeah. So similarly, yeah, it's gonna, the previous peak was here. Okay, over here. So it's basically like this. Like this, okay? So that's that. And yeah, I wanted to use a different color for this because what's the logic? Let's use blue. What's the logic? What does the blue section denote? The blue section denotes the capacitor charging up, and the pink section denotes the capacitor discharging. You need to draw the pink and blue sections to get full marks. So this was tricky. In fact, it was tricky. And you could draw straight lines instead. They'd give you full marks. Calculate the capacitance of the capacitor. Now, this is the new topic that was added to the syllabus. Discharging a capacitor. So, the capacitor loses 10% of its voltage. So if you lose 10% of your voltage, how much is left? 90%, right? So what's the formula for discharging a capacitor? It's basically V is equal to V naught. V is equal to V naught e to the power minus t by RC. Okay? So V is equal to V naught e to the power minus t by RC. This is the formula. All right? So there are multiple ways in which you can do this. So the first one is, we know that the final V is like 10% less than V naught, which is 90% of V naught. So that's 0.90 times 6.0, which is 5.4 volts. Okay, so we can write that. Or honestly, I just go for 90 by 100 times V naught is equal to V naught e to the power minus T by RC. We could get rid of this, okay? But they do something really lame. I don't really like this in the mark scheme. I'm just seeing it. So they write down the actual values. You get what I mean? Like they do this. 5.4 is equal to 6.0 e to the power minus T by RC, you know? So 5.4 by 6.0, if you do that, 5.4 by 6.0, that is 0.90. You guys do know that, right? E to the power minus T by RC. So what is this T? So this T is how long the change occurred, how long the discharging occurred. So how long did the discharging occur for? If we think about it properly. Whoa, wait. So this is when the discharging started, and this is where it ended, you know? This is where it ended, over here. Exactly over here. So it started at 0.02 and it ended at 0.05, 0.054 actually, 0.054. Okay, so I was delving too deep. This is where it ends, 0.54. You can see it in the other ones clearly. Like for example, you can see it in this one. It starts at 0.0. Wait, why did I write 0.02 here? This should be 0.06. My bad, my bad. Sorry for this labeling. There's an error. Okay, so it starts at 0.06 and ends at the discharging ends at here. This is 0.09, 0.094. So think about it. It started at 0.06 and ends at 0.094, or it starts at 0.02 and ends at here. This is basically 0.054. This is 0.05, so 0.054. So what's the difference? 0.054 minus 0.02 gives you a value of 0.034 seconds. So that is the discharging time, 0.034 seconds. So this was a bit tricky, okay? You needed to figure that out, the discharging time. All right, could I clarify? That's the discharging time. So if you input the values correctly, the pen is glitching. Give me a sec. Yeah. So the discharging time is, suppose 0.054 minus 0.02, which is 0.034. So 0.034 minus 0.034 divided by RC, where R is the resistance in the circuit and C is the capacitance. So R is basically, you know, 1200, and C is unknown. C is unknown. So that's 1200 times C, which is unknown. So to deal with sounds with E, we use ln, right? So ln 0.90 is equal to, if we use ln E, that's 1, 0.0 minus 0.034 divided by 1200 C, okay? Or 1200 C is equal to minus 0.034 divided by ln 0.90. Let's do that. 0.034 minus answer divided by ln 0.9. So that's 1200 C equals to 0.3227 divided by 1200. That is, C is equal to 2.69 into 10 power minus 4. Okay, so how many significant figures though? Since our data is 2 SF minimum, the time is 0.034 and 5.4 volts, we're going to go for 2.7. So that's 2.7 into 10 power minus 4 farads. Really difficult, really difficult. So many students would lose these last 2 marks, okay? So tricky. So Cambridge is increasing the difficulty, it seems, over time. And this was a new topic that was added to the syllabus, right? That is why it was a tad bit difficult. So let me know in the comments if you still don't understand. But it was quite difficult, yeah. So you need a good understanding of alternating current and smoothing to figure this one out. You can't do this with capacitors only. Okay. Moving on to number 6. Define magnetic flux. Basically, they want us to define phi. So remember that phi is basically BAN or BA. That is magnetic flux. What is magnetic flux? Linkage. That's BAN multiplied by the number of turns. So magnetic flux is basically B times A. That's magnetic flux. B times A, and if you do BAN, that's magnetic flux linkage. Okay. So it's either BA or BA cos theta, but we can mention that in the beginning. Okay. So magnetic flux is basically the product of, what is this B? Magnetic field strength or magnetic flux density? So it's the product of magnetic flux density and area. It's actually cos theta, but we assume that the theta is 90 degree. Sorry, BN sine theta, right? My bad. BAN sine theta. So we need to ensure that where area is perpendicular to the magnetic field. Okay. So product of magnetic flux density and area, where the area is perpendicular to the magnetic field, we assume that this theta is 90 degrees. Alright. Next, a square coil of wire of side length 12 cm consists of 8 insulated turns. The coil is stationary in a uniform magnetic field. The plane of the coil is perpendicular to the magnetic field as shown. Okay. We have magnetic field lines into the page and a square coil of 8 turns. The flux density of the magnetic field varies with time shown. Determine the magnetic flux linkage inside the coil at time 0.60. Give a unit for your answer. So at 0.6 seconds, we need to find out the flux linkage. So the formula for flux linkage is basically BAN. So magnetic flux linkage is basically N times phi, which is BAN. So that's N times BA, right? So the B at 0.6 is 400 millitesla. So 400 into 10 to the power minus 3. The area of the coil. What is the area? It's basically a square, right? So the area is essentially this. So 12 into 12 or 0.12 into 0.12, right? So that's basically 0.12. 12 in meters is 0.12. The area of a square is length square, right? So 0.12 square into the number of turns, which is 8. So we're getting an answer of 0.046. 400 into 10 power minus 3 times 0.12 times 0.12 times 8 is 0.046. So the unit of flux linkage is, actually think about it, Webers. The unit is Webers. So for flux and flux linkage, we have the same unit, which is Webers. All right. So the unit is Webers, and the value is 0.046. Area times magnetic field strength or flux density times the number of turns. State how 612 shows that the EMF induced across the terminals between 0 and 6.6 seconds is constant. So you guys know something, right? According to Faraday's law, the EMF induced is proportional to or equal to the rate of change of magnetic flux linkage. Okay. So as you can see, everything else is constant, right? The number of turns is constant, the area is constant, and B isn't constant. B is changing. So if B wasn't changing and EMF wouldn't be induced, and B is changing at a constant rate with time. Since the gradient of this graph is an indirect indication of the EMF induced, since the gradient is constant, this is why the EMF induced will also be constant. So mainly this is because the line is straight, or since the graph is a straight line. Okay, that's how. So calculate the magnitude of E. So I was telling you guys that EMF, right? The EMF is this is actually the induced EMF. Okay, so the induced EMF is equal to the rate of change of magnetic flux linkage. So that is N, this is del N phi divided by del T. So what's the change in magnetic flux linkage? Like initially it was 0, right? Initially it was 0. From 0 it became 400, and the change was 0.046. So the change was 0.046, and the time taken was 0.60 seconds, which gives us an answer of 0.077 volts. Okay, 0.077 volts. Now the procedure in B is repeated, but this time the terminals of the coil are connected together. So the procedure is repeated, but these terminals are apparently connected together. Okay. Sterling explained the effect on the coil of connecting the terminals together during the change of magnetic flux density shown in 6.2. Okay. So this is interesting. This is interesting. In this experiment, the previous one, the terminals weren't connected, right? They were kept apart. Now we do connect them together. Now state and explain the effect on the coil of connecting the terminals together during the change of magnetic flux density shown in figure 6.2. This one from 0 to 400. Okay, let's see. So basically, when the coil wasn't, when the terminals weren't connected, there was no current flowing in the coil. Because remember, for an EMF to be induced and for current to flow, the terminals must be connected. Since they were not connected initially, no current was flowing. But if you do connect them, what's the first effect that's going to happen? Current will start flowing. Okay. So what if current flows? Basically, when current flows, you know that the coil has resistance, right? So the work will be done against the resistance of the coil. As a result, the temperature of the coil will rise. So that's what we're going to see. So that is one way of answering it, or you could opt for this. You could say the current in the magnetic field. Since there's a current flowing here, okay, since there's a current flowing here, it is in the presence of another magnetic field, right? So the coil will now experience a force. Okay. Since current is flowing in the coil now, it will experience a force. Now remember that according to Lenz's law, the EMF will be induced in such a way, such as to oppose the change causing it. Do you understand? So since the magnetic field lines are traveling into the page or are directed towards the page, how would this actually affect our coil? We need to understand that. Okay. So we can say the current in the magnetic field causes forces to act on the coil. We'll get 1 mark for that. Now we need to say how. So the opposite sides of the coil are forced inwards. That's what happens. Okay, so let me explain this. So the first mark is the induced EMF causes current flow in the coil. So we get 1 mark for this. This is our first mark. Now we get access to the other options. I would personally go for the current causes dissipation of energy in the resistance of the coil. So temperature of the coil rises. This is one route. We get 2 marks for this. Or an alternate option is you could go for current in the magnetic field causes force to act on the coil, and we need to say how it affects it. The opposite sides of the coil feel a force inwards, or you could say are forced inwards. Okay, so the opposite sides of the coil are forced inwards. So what does this mean? Right, so if we use our left hand rule for different sections, suppose current is flowing like this. Suppose we don't know current is flowing like this. So I'm pointing my index finger into the page and my middle finger to the right. I'm pointing my index finger into the page and middle finger to the right according to this direction. My thumb is pointing towards this side. This is the thumb, my thumb's direction. And for the upper part, upper section, if I point my index finger in and my middle finger to the right, the force is pointing towards this side. What about this end, the one on the right? If I point inwards, force is pointing to the left, and in this direction, force is pointing to the right. Okay. So as we can see, the force is pointing inwards for all cases. Oh, so that's what they mean by the opposite sides of the coil are forced inwards. So this is it basically. Okay, but what if I just chose opposite directions? What if instead of this, what if I went for this instead? What if this was F? Would this work as well? I mean, this is the direction of the current. Let's see. So this would be out. This would be out. This would be out, and this would be out. So how are we sure that it's gonna be inwards? The one I drew initially was right. So this is the correct diagram. This is the correct diagram over here, where current is pointing in this direction, like this. So here, if you use your Fleming's left-hand rule, index finger into the page, middle finger to the right, force points here. For all of them, force is pointing like this. So it's like the square will be crunched up inside. All the opposite sides will feel a force inwards. So it's going to be like this. But my question is, how are we sure that the direction of the current is in this side? Is there any way we can confirm? We don't know the positive or negative terminal either, right? So the procedure is be repeated, but the terminals are connected together. Magnetic field into the page. I actually have no clue how this happened. Plane is. I actually need more info. So if I do find out how, I'm gonna let you guys know. All right. Like how this happened, why it's pointing to the right, but this is the solution, so this is why it happens. So when we connect the terminals, a current is induced which apparently flows in this direction, and if we apply Fleming's left hand rule on each side, we see that the force is pointing inwards towards a common point, which actually forces the opposite sides inwards. Okay, interesting. But why like this, I'm not sure. I'm not sure why it's flowing like this. I do not know. I need to look into it. All right. Maybe because the convention is to the right. I really don't know. That was what I thought initially. I'll let you know in the comment section. All right. Okay. Let's move on to number 7. So what is meant by a photon? A photon is basically a quantum of energy. That's one mark of electromagnetic radiation. Okay. Now B. Electromagnetic radiation of a varying frequency and constant intensity is used to illuminate a metal surface. At certain frequencies, electrons are emitted from the surface of the metal. The variation with f of the maximum Ke of the emitted electrons is shown. State the name of this phenomenon. So this is basically photoelectric effect, where after a certain frequency, when you emit photons on the surface of a metal, electrons are emitted when you illuminate a metal. But below that frequency, no electrons will be emitted, right? So that minimum frequency is called the threshold frequency. So describe 3 conclusions that can be drawn from graph 7.1. The conclusions may be qualitative or quantitative. So what do we see, guys? That as we increase frequency, Emax is also increasing, right? So Emax increases linearly. This was optional. With increasing frequency. Okay, next. We can say that there is a frequency below which no electrons are emitted, right? Or you could just say that the threshold frequency is 5.4 into 10 power 14. Okay, we could say that threshold the threshold frequency is 5.4 into 10 to the power 14 hertz. All right, what else? You guys know the equation of this graph, right? So basically, HF, the energy of the photon, is equal to the work function plus Emax. Okay, so if we rearrange it to Emax is equal to HF minus phi, we get the equation y is equal to mx plus c, where the gradient of this graph is actually h. This is our gradient, and the intercept is minus phi. Okay, so what is the gradient of this graph? It's the Planck constant. So the gradient of the line is the Planck constant. Or you could go for something quantitative, like you could actually find out the gradient. Like, suppose this point, how much is this? This is 11.4, right? So this is 11.4 into 10 power 14, and that's 4 into 10 power minus 19. Similarly, this point is 5.4 into 10 power 14 and 0. So basically 4 into 10 to the power minus 19 minus 0 divided by 11.4 minus 5.4 into 10 power 14. If you do find out the gradient, 4 into 10 power minus 19 divided by 11.4 minus 5.4 into 10 to the power 14, which is 6.67 into 10 power minus 34. You could say that, okay? So you could say that the gradient, you could say that the gradient of the line is 6.7 into 10 power minus 34 joules second. Okay, what else? There was another point. We could talk about the work function. Basically, what am I talking about? This phi over here. What is this phi? It's basically our y-intercept, right? So how to find out the y-intercept? Basically, when this value is 0, when frequency is 0, we can find out the value of y-intercept. Okay, so basically when f equals to 0, when f equals to 0, E max is equal to phi, which is a negative value. So this could be done by extrapolating this line and seeing where it cuts the x-axis, at the y-axis I mean. So that's one way of doing it. Okay, so that's why there was an alternate answer here. They allowed the work function of the middle is 3.6 into 10 to the power minus 19. 3.6 into 10 power minus 19. Okay, so the work function of the metal is 3.6 into 10 power minus 19 joules. Okay, so we need to extrapolate that to find it out, the y-intercept. Or since you know the gradient, you could find out using any point. For example, check this. I know that this is one coordinate, right? And E max is equal to HF minus phi. So why don't I do this? Why don't I write E max, which is 0, is equal to, I'm using this point, is equal to 6.67 into 10 to the power minus 34 times 5.4 into 10 power 14 minus phi. So what is the value of phi? Answer into 5.4 into 10 power minus 14, which is phi is equal to 3.6 into 10 power minus 9. That's how they did it basically. Okay, or you could convert it to electron volts, which is 2.2 electron volts. Okay, that's another answer. Now the experiment is repeated twice, each time making one change. State with the reason how the graph would compare with figure 7.1 when a different metal is used but keeping the intensity of radiation the same. So when you change the metal, basically the threshold frequency changes. Okay, so if you change the threshold frequency, basically it won't be 5.4 anymore, it would be greater or less, but everything else would remain the same. Do you guys understand? So there will be a different threshold frequency, all right, and the line has the same gradient, okay, but different intercept. So the different intercept indicates a different work function. Okay, different work function. So if the line was, it could have been like this, parallel, but the x-intercept would be different and the y-intercept would also be different, right? Because the y-intercept represents the work function while the x-intercept represents the threshold frequency. Now the same metal is used, but with intensity, with electromagnetic radiation of intensity 2y. So the, you know, basically what's gonna happen is this graph, think about it, it totally depends on a few things like work function, which is the x-intercept, sorry, the y-intercept, h, which is Planck constant. This doesn't change, you know, it has constant in its name, it doesn't change. So really there would be no change. This was just a trick question. Changing intensity doesn't have any effect on the graph. So the photons have same energy. Okay, so the line would be unchanged. So this was tricky, but the key point is we used electromagnetic radiation of double the intensity. So what was the question over here? Electromagnetic radiation of a varying frequency and constant intensity is used to illuminate a metal surface. So intensity depends on the number of photons per unit time and the frequency. Okay. So as we increase frequency, do you know what happens? As frequency increases, energy increases, right? So to keep intensity constant, as frequency increases, the number of photons per unit time decreases to keep the intensity constant. Here we used twice the intensity. So maybe the number of photons per unit time changed. Do you guys get it? Like the number of photons emitted per unit time. But that has nothing to do with the graph. The graph only depends on the work function of the metal, which depends on a specific metal, and the Planck constant, which is a constant. So it wouldn't really change, okay? So the gradient of this line doesn't change. Please remember that. Because the photons have the same energy. Because photons, the energy depends on E is equal to HF. And H is a constant. We would just be varying the frequency. Frequency in what sense? Like, basically, the H, it's independent of frequency. Planck's constant is independent of frequency. Okay. So even if the intensity is changed, the energy will be constant. I'll show you how. Like you guys might be thinking, if you change frequency, energy is supposed to change, right? So how do they have same energy? So for example, how is intensity calculated? For I, for example, if we have um, a certain frequency, for that frequency each photon has an energy of 10 electron volts. Suppose we had 5 photons, that would give us an intensity of 50, right? Now for twice the intensity, what could we do? Each photon could still have the same energy, right? But we'd have 10 photons per unit time instead. That would give us an answer of 100. But the number of photons doesn't really have an impact on this graph. Okay, the main thing was we used the same metal, so the intercepts wouldn't change, the threshold frequency. Okay, since we use the same metal, this phi and this f doesn't change. If that doesn't change, your line will be passing through the same 2 points, so it will be an unchanged line with the same gradient. Okay, so the line remains unchanged. Why? Because we're using the same metal, it has the same threshold frequency, so photons would need the same energy to uh, you know uh, emit electrons from the surface of the metal. But what does intensity do really? Intensity usually changes the number of photons arriving on the plate. So what would change? The number of electrons emitted per unit time, okay? But that's not important here. Number 8. Last 3. What is meant by nuclear binding energy? So it is defined as the energy required to separate the nucleons in the nucleus. We get 1 mark for that. To infinity. Okay. On figure 1.8, sketch a line to show the variation with nucleon number of and binding energy per nucleon number. So this is 250, right? So the midpoint should be 125, and this midpoint should be, how much is it? That's 62.5. Okay. This midpoint is 62.5. So you guys know, right, that the highest iron 56 has the highest binding energy per nucleon. Okay. So it's like this. We don't say that hydrogen has a binding energy of 0. It does have some binding energy per nucleon. So the peak is at 56, alright? The peak will be at 56. The line should start close to the origin. The peak should be at 56, and then it just decreases as you keep on going forward, okay? So the highest point, the most stable point is iron 56, understood? So there should be a steep line on the left hand side and the shallow line on the right hand side till 250. This is how it should be drawn. How did I know this? I found out where 56 is, and I know that Fe56 is the nucleon with highest binding energy per nucleon, okay? That's how. Then I just plotted this graph. And I know that hydrogen and helium start close to 0. That's how. In one type of nuclear process, deuterium undergoes this reaction. This is a nuclear fusion. Nuclear fusion. Explain with reference to your line in A2 why this reaction results in the release of energy. Okay. So think about it. Both of these are at 2. 2 is located somewhere over here. 2 is located somewhere over here. They are on the left hand side of the graph. So remember that both fusion, for fusion we go from here to here, and for fission we go from a bigger nucleus to smaller nucleus. We basically want to be like iron 56. Everyone wants to be like iron 56. Either you can go from left to peak or from the right hand side to the peak, okay? So explain with reference to your line in A2 why this reaction results in the release of energy. Mainly because they have low A values of 2, but helium 3 has a higher value, like 3 is over here. So ultimately the end goal of nuclear fusion or fission is to get a nuclear number closer to 56. Do you guys understand? That's the main logic behind this. So let's write it down. Essentially we can say that both particles have low A values of 2, or we could say that both particles are at the left hand end of the graph, okay? So why is this important? Helium 3, right, has a higher binding energy per nucleon than H2. So think about it. Binding energy is the energy required to separate the nucleons in the nucleus to infinity. So since helium has higher binding energy than the hydrogen atoms on the left hand side, obviously this reaction will, release some energy. Why is that? Think about it. So the best way to find this out is actually, by using the mass defect. We could find out the mass defect, and you would see that the mass is actually smaller on the right hand side. We know that in any nuclear reaction, mass energy is conserved, right? So you would see that the mass on this side is greater than the mass on this side. So does that mean that mass was lost? No. Some mass was simply converted to energy. The sum of these two things are conserved as a whole. So the main reason why a fusion reaction releases energy is because the total mass of the resulting single nucleus is less than the mass of the two original nuclei. Do you guys understand? Since the mass of the resulting nucleon is less than the mass of the initial nuclei, obviously some mass has been converted to energy. So you can answer this in terms of binding energy. It's the other way around. Having high binding energy means that more mass was sacrificed. Do you get it? So the particles on the left have low binding energy, which means the mass wasn't sacrificed to hold them together. But to hold helium together, more mass needs to be sacrificed. Do you get it? So there is a higher mass defect to get this higher binding energy per nucleon, which releases energy in the process. Okay, that's all. Number C. Calculate the energy released when 1 mole of deuterium undergoes the reaction. This is perfect because now we have the data. Right, so let's go for that. So let's find out the mass defect, shall we? So we had hydrogen 2-1. This resulted in helium 3-2 plus a neutron. So let's find out the mass defect, yeah? So the mass defect is for helium, the on the left hand side, the total mass should be 2 into 2.0141 2.014102, and on the right hand side it's 3.016029 plus 1.008665. Please add this up. 2 into 2.014102, which is 4.028204 minus 3.016029 plus 1.008665, which is 4.024694. Which one is greater? Clearly the one on the left hand side, right? So if you find out the defect, 4.028204 minus calculate answer, the defect is actually 3.51 into 10 to the power minus 3. Now to find out the energy released, we're going to opt for E is equal to del mc square, which is 3.51 into 10 power minus 3 times 3.00 into 10 to the power 8 whole square. Okay, so 3.00 into 10 to the power 8 whole square, which is 3.159 into 10 to the power 14. Okay, so the mass is in U, by the way. The mass is in U. So this value that we get, 3.159 into 10 to the power 14, this is not in joules, by the way, because the mass is in terms of U. So if you want to find in joules, you have to use the SI units, obviously. So what's the SI unit? 1 U is basically 1.66 into 10 to the power minus 1.66 into 10 to the power minus 27. Okay, so we need to multiply this 1.66. Wait, let me show this at once. Into 1.66 into 10 to the power minus 27 times 3.00 into 10 to the power 8 whole square. Okay, so that's 1.66 into 10 to the power minus 27. That gives us this value of 5.24 into 10 to the power minus 13 joules. Now, this isn't the end. It's worth 5 marks. Okay, so we found out the energy released for one molecule of this. Okay, one molecule of helium being formed. Now, think about it. When 1 mole of deuterium undergoes this reaction, this is important. We have 1 mole of deuterium. What does that mean? 1 mole of both of these combined. So how can we divide 1 equally? That is basically 1 divided by 2, which is 0.5 moles of each. So 0.5 moles of this and 0.5 moles of this react together to form 0.5 moles of helium, right? So how many helium molecules are there in total? So the total energy is 5.24 into 10 power minus 13 into 0.5 moles of helium, which is 0.5 times the Avogadro constant, 6.02 into 10 to the power 23. Do you get it? So into 6.02 into 10 power 23 into 0.5, which gives us an answer of 1.58 into 10 power 11. Okay, joules. So I'm going to repeat the process again. The mass on the left hand side is greater. So I found out the mass defect, found out the energy in joules by converting U into kg. Now this energy was for the release of 1 helium nucleus, but we have 1 mole of deuterium, right? We have 1 mole of deuterium. One combined, so to react them equally we are going to react 0.5 of each, right? So according to the molar ratio, we are also getting 0.5 moles of helium. That's why I multiplied 0.5 into Avogadro constant to find the number of molecules of helium which were formed into the energy for 1 helium atom produced. That's it, 1.5 into 10 power 11. That's all, guys. Okay, that was tricky. Moving on to the last 2 questions. Let's go. Explain how X-rays are produced and used in medical diagnosis. Really important. Remember that we bombard high-speed electrons. So electrons are accelerated by an applied potential difference, right? Then they hit a target metal. electrons hit a target metal, then they are decelerated suddenly. So this sudden deceleration creates a lot of energy. So X-rays are produced when electrons decelerate suddenly. Okay, that's the source of energy. Statewide X-ray images are taken on multiple sections. Basically, X-ray is a 2D image. Okay, so CT scanning is basically a 3D image. So basically, images of the multiple sections are combined to create a three-dimensional image. That is why. Okay, an X-ray image is taken of the structure shown in figure 9.1. The linear attenuation coefficient of bone is this, and of tissue is 0.89. The incident X-rays are parallel and have uniform intensity. Determine the intensity of the digital X-rays at point P. Okay, so here we're only passing through soft tissue, 0.89. So the formula is I is equal to I naught e to the power minus mu x. Okay, so I is equal to I naught times e to the power minus, the distance is 5.6 and this is 0.89. Oh yeah, we need to check whether it's in centimeters. It is in centimeters, so do that. E to the power minus 5.6 into 0.89, which is I is equal to, or I by I naught. Oh, it's in terms of I naught, right? So I is equal to 6.85 into 10 to the power minus 3 times I naught. So we're going to get the answer to 2SF, obviously. So that's 6. Wait, 0.89. 0.89 into 5.6. 6.8. Okay, we can't do it twice. Basically, it's 6.8466 times I naught, which is I is equal to 6.8 into 10 power 3, sorry, minus 3. So that's 6.8 into 10 power minus 3 I naught, or you could just say I is equal to 0.0068 I naught. Okay, so 0.0068 times I naught. Now what about point Q? Here we're passing through soft tissue as well as bone. So if bone is 2.4 centimeter, 5.6 minus 2.4, 5.6 minus 2.4, that's 3.2 centimeters of soft tissue. Okay, so for bone it's 3.4 per centimeter. Let's do this. For two media, it's going to be multiplied. Okay, that's how it happens. So I is equal to I naught times e to the power minus, for the soft tissue it was 3.2, so 3.2 times 0.89, also times e to the power minus 2.4 centimeters times 3.4. That's the coefficient. So let's do that. E to the power minus 3.2 into 0.89 into e to the power minus 2.4 into 3.4. That gives me an answer of I is equal to 1.6569 into 10 to the power minus 5 I naught, or that's basically I is equal to 1.7 into 10 to the power minus 5 I naught. Okay, so 1.7 into 10 to the power minus 5 I naught. Great. Explain with reference to your answer whether the X-rays have good contrast. So to have good contrast, okay, what you need is between two sections of the journey, this section where we pass through two types of media and another section where we pass through soft tissue, we need vastly different detected intensities. For example, if you compare these detected intensities, 0.0068 divided by this answer over here, the one detected at point P is 410 times greater than the one detected at point Q. What does that mean? What does that mean? Isn't it much greater? So we should say that the image has good contrast Why? We had a similar question in March 5, 2022. If you guys want to see, wait, let me show you. The question in February, March 2022 was very similar. Wait, let me show you. But there we talked about the linear, attenuation coefficient. Here we aren't talking about that. We're just talking about this, because we can say that in the mark scheme they just said comparison of intensities or values in B. They're talking about these values. You could talk about those, or we could just say that the image has good contrast because the intensity at point P is much greater than intensity at point Q. That's all. Or you could say that the value of attenuation coefficient for the bone is much greater than the attenuation coefficient for soft tissue. That's all. Okay, so it has good contrast. If they were similar, the image would have bad contrast. All right. Okay, guys, on to our last question then. Let's begin. So starting with Wien's displacement law. So what does Wien's displacement law state? It states that the wavelength. So this is important for you guys because we don't have much content from astronomy. We only have specimen paper and February, March 2022. So the wavelength, this is the first time I'm saying this. So the wavelength of maximum intensity is inversely proportional to the temperature in Kelvin, or the thermodynamic temperature. Okay, so the wavelength of maximum intensity is inversely proportional to the thermodynamic temperature. Basically, we say that lambda max is inversely proportional to 1 by T. This is Wien's displacement law, and we do get a constant. So we had to use this in both the previous variants, okay? March 5, 2022, as well as specimen paper 4. Let me show you, then it will make more sense. So check this. This is Wien's displacement law. The temperature at the surface of the star is inversely proportional to the maximum wavelength emitted. So we can actually get a constant, right, by multiplying them. So that's the law, that the wavelength of maximum intensity is inversely proportional to the thermodynamic temperature. All right, please remember this. So if you do cross multiply them, we get lambda max, the wavelength of maximum intensity, into temperature is equal to a constant. We can use this to find out the wavelength and temperature of different stars at the surface, of course. Now we are seeing two stars. So which wavelength should we consider? Only the wavelength for maximum intensity. Okay. So similarly here, we need to look at the wavelength which has maximum rate of emission. So for here, the maximum emission is over this side. So it's over here, I guess. Yeah. Okay. So determine the surface temperature of star B. The surface temperature of A is known as 5800 Kelvin. Okay, let's do that. So what are the values for star A? It's 0.5, and for star B, this is 0.6, this is 0.7, so it's in the midpoint, which is 0.65, right? Okay. So lambda max for star A is 0.5, lambda max for star B is 0.65, okay? Micrometers. So let's do it. We know that according to Wien's displacement law, lambda max times temperature is equal to a constant, or is we could say the lambda max is inversely proportional to 1 by T. So we can go for this 0.50 times 5800, this is for star A, is equal to 0.65 times the temperature for B. I'm not converting the micrometer because it's going to cancel out. 0.5 into 5800 divided by 0.65 is, the temperature of B is 4461. Since our minimum our minimum significant figure is 2, we're gonna go for a 2 sig fig answer, which is 4500 Kelvin. Okay, 4500 Kelvin. That's all. Last part. Star B appears less bright than star A when viewed from the Earth. Use figure 10.1 to suggest with the reason how else the physical appearance of star B compares with that of star A. Okay. Star B compared to star A. So visible wavelength. How much is that? 400 to 700 nanometers, right? That's our visible wavelength. So for star A, the wavelength of maximum emission was 0.5 micrometer, which is, try doing it. Micro is 10 power minus 6 and nano is 10 to the power minus 9, right? So zero point 0.5 times 1000 gives us the uh, wavelength in nanometers. That's 500 nanometers, right? What about star B? The maximum is 0.65 micrometer, which is basically 0.65 times 1000 is 650 nanometers. Okay, so according to the visible light spectrum, it's Vibgyor, right? So we mainly compare blue and red light. So blue is at around 400, while red is at around 700. So comparatively, A would look bluer, and B we could say it looks redder. It's more red comparatively. Okay, so that's the main thing that we'd see. So how would it look when we see it from Earth? So basically, star B has a greater peak, or we could say average. I'd go for peak, greater peak wavelength. All right. So what does this result in? As a result, star B looks more red or looks redder. This is what they said. Okay, it looks redder. Now the lines in 10.1 have been corrected for redshift. Okay, what's redshift? We know that the universe is constantly expanding, right? The universe is constantly expanding. So as objects are moving further away from us, the Doppler effect is occurring. So when an object goes away from you, for example, the ambulance which is going away from you, the Doppler effect occurs and wavelength increases essentially. So compared to the actual one, compared to the original frequency or the original wavelength, the observed wavelength would be greater, or it would be more red essentially, right? So what is meant by redshift? What is this? So we have two forms of uh, wavelength according to Doppler effect. One is the frequency or the wavelength of the source, and the other is the observed or apparent wavelength. Okay, as you can see in the formula for Doppler effect. Where is it? This is the Doppler redshift formula. But where's the formula for Doppler effect? Wait, here. So Fo is the observed frequency and F is the frequency of the source. The relative, due to relative movement of the source and observer, the observed frequency or the apparent frequency is different. Similarly, since the planet is moving away, compared to the frequency or wavelength of the source, the apparent wavelength is greater actually. Do you guys understand? That's the thing that they're talking about here. So, what is redshift? Redshift is basically like this. The apparent, sorry, the apparent wavelength is greater, or you could say that the wavelength is greater than known value. Why? Due to, I was saying, due to movement of star away from the observer, us on the Earth. Okay? This is very, very important. And blue shift is not possible because the universe is expanding. Okay, so only redshift occurs. Explain how cosmologists are able to determine that light from a distant star has undergone redshift. Okay, so this is really important. So basically, we do it in the lab. So cosmologists do what exactly? So cosmologists examine the lines in the spectrum. So I'm basically talking about quantum physics over here. You know there are two types of spectrum, right? Absorption and emission spectra. Okay. So emission is from a hot object, a star basically. So cosmologists examine the lines in the emission spectrum of light from the star and with compare the lines, and compare the spectrum with a known spectrum. So what is essentially happening here? In the Marx scheme, they've said that by examining the lines in the spectrum of light from the star, I wrote this in a different way. Let me write the Marx scheme answer so it will match more with you guys. But you could write it like this as well. So let me explain meanwhile. So they wrote by examining the lines in the spectrum of light from the star and comparing with known spectrum. Okay. So suppose we know that the composition of a star is made up of helium, hydrogen, and so on. So typically for the known spectrum, we know that for hydrogen it should be around 420 nanometers, and for helium it should be around 500. But now if we examine the spectrum from the distant star, and we know that the composition is the same. Okay, we know the composition is the same. For hydrogen, we are going to be seeing that the wavelength, rather than being 420, the absorption spectrum looks like this. We'd see a line over here at 420 at 500. It would instead be 450, while helium would be like 570 or something. So what happened really? This is the known one from a known star, or basically not a known star. Basically, like if we analyze the spectrum of hydrogen and helium in the lab, we would get this is in the lab. Now from the star that's distant, when we compare it, we're going to see that the corresponding wavelength is going to be a tad bit further. What happened? It feels as if it has moved to the right, or wavelength has slightly increased, and this is due to the Doppler redshift. But to do this, obviously, we need to know the composition of the star to compare it with known elements, okay? And this is mainly an emission spectrum. All right. So, guys, that's it. Thank you for watching. This was variant 4.1 or 4.3. It was an overall, it was a more or less a very difficult paper overall, which explains why the Marx scheme, the threshold was so low at 59. Okay, there were common questions, but there were hard questions as well. So yeah, from 2022 it's gonna be difficult because the pattern has changed. I had a feeling that the pattern would change, so you have to practice harder. All right, so good luck with that. Hopefully this helps you next year. So I'm gonna link the paper for May-June 2022, variant 4.2 up here. I'm going to link the playlist for paper 4 up here, and I'm going to link the paper for Feb-March 2022 variant 4.2 down here. And remember to subscribe to the channel if you like the content. See you guys in the next one.